Hey guys, welcome to chapter 18. In chapter 18, we're going to study something called thermodynamics. It might sound similar to something that we studied in Gen Chem 1. So we studied thermochemistry. So that was the heat of chemical reactions. Now we're going to study thermodynamics, which is a little bit broader of a category. And thermodynamics is really the study of energy and its interconversions. So the study of energy and its interconversions. So let's think about some questions. So if you puncture a tire, so you're driving down the road, you run over a nail, it creates a hole in your tire. Does your tire inflate, so get more air in it, or does it deflate and go flat? Yeah, it deflates, right, and goes flat. Well, why? I don't know. Let's say that old nail was sitting on the ground before you rode over it. So you have an old nail on the ground. Does that nail get rusty or does that nail get shinier? Yeah, it typically rusts, right? And then we've got a tray of ice cubes. So we take it out of the freezer, we put it onto the desk. We wait a couple hours. Are those ice cubes going to stay frozen ice cubes, or are they going to melt and go from a solid to a liquid? Okay. So all of these processes that I've introduced, so deflating tire, rusting nail, melting ice cubes in room temperature, are all what we call spontaneous reactions. And what we're going to answer by the end of this chapter is, why do these things happen the way that they happen? Why does a nail get rusty instead of shiny? So a spontaneous reaction is a reaction that occurs without any outside intervention. So it may need a little spark to start it. It may need a little push to get going. But once it has that little spark or that little push, it will continue to happen without any outside intervention. So think about a bike at the top of a hill. If you kind of nudge over the top of that hill, your bike will continue to go down that hill without you moving your feet, without you having to pedal that bike at all. It'll just spontaneously fall down the hill or roll down the hill, right? No outside intervention needed. A non-spontaneous reaction, so this is the opposite. A non-spontaneous reaction is a reaction that will occur as long as energy is continually being put into the system. So if you think about the same analogy with a bike going up a hill, in order to make that bike continually go up the hill, you've got to continually pedal, or you've got to push the bike by walking it up the hill. So the bike won't just randomly go up a hill without any assistance. There's going to be some energy that has to be continually added in order for it to go up the hill. Non-spontaneous does not mean it's impossible. So it is possible to take a bike from the bottom of a hill and put it on the top of a hill. That is something that we can do. So it's not that non-spontaneous equals impossible. Non-spontaneous just means it needs some assistance to get up the hill. Okay. Some things just to tie in from things that we've learned. So reversible reactions. So remember, we have a forward reaction and a backwards reaction. In those reversible reactions, one direction would be spontaneous. The opposite direction would be non-spontaneous. So both of those are inverses of one another. So if one way is spontaneous, then the other way has to be non-spontaneous. Okay. And then before we move on and dive deeper into spontaneity, let's just get rid of some misconceptions right away. So I've already addressed one, the fact that non-spontaneous does not mean impossible. A couple other misconceptions is that spontaneous doesn't necessarily mean fast. So you can have something that is a spontaneous reaction, but kinetically, the reaction takes a really, really long time. So an example of this is diamonds. So diamonds are just a collection of carbon atoms. Graphite, so the lead in your pencil, is just a collection of carbon atoms. So it is a spontaneous reaction for diamond to break down into graphite. So the diamond that's on your finger or in your jewelry can spontaneously break down into pencil lead. Well, thankfully for us, that is a very, very slow process. So the diamond that my husband bought for me is not going to become graphite in my lifetime or my kids' lifetime or my grandkids or great-grandkids, but eventually, somewhere down the line, it will become graphite. But thankfully, that is not a fast reaction. As I said before, it may need a spark. So it may need a little something to get it going. But once the engine is turning, once the wheels are turning, then it will continuously happen on its own. And then lastly, it can be endothermic or exothermic, and we'll see that pretty quickly. A lot of spontaneous reactions are exothermic, so we will see that statement is true and that a lot of them are exothermic, but there certainly are spontaneous reactions that are endothermic. So we will take a look at a couple examples of that because it is a bit counterintuitive. But spontaneous reactions can be endo or exothermic. So don't tie those two together. So let's take a look at what is entailed in a spontaneous reaction. So there's two factors that determine whether it's spontaneous or not. There's enthalpy and entropy. Enthalpy and entropy. So two very sciencey words there. Enthalpy is something we've already looked at. So enthalpy we saw at the very end of General Chemistry 1. So enthalpy is the difference between the heat of the reactants and the heat of the products. So remember when we studied energy for chemistry, typically the form of energy that we study as chemists is heat energy or thermal energy. And we introduced this idea of enthalpy. So delta H was the difference in the heat of the reactants and the products. And that's where we had endothermic, heat is entering the system. Exothermic, heat is exiting the system. So certainly enthalpy is a piece of the puzzle, but it is not the whole story. We also have this new variable called entropy. So we'll spend a little bit of time getting to know entropy before we start quantifying it. So entropy is defined as the difference between the randomness of the reactants and the randomness of the products. So I will often talk about, instead of randomness, I'll talk about messiness. So messy is good in chemistry. Okay. So real quick, let's just review enthalpy before we dive into entropy. So enthalpy, if it is endothermic, energy is being absorbed by the surroundings or energy is entering the system, and the change will be a positive number. We have to put a deposit of energy in. So reactants are low in energy, products are high in energy, and to climb the ladder, we've got to put energy in. For exothermic, energy is being released into the surroundings. So exothermic, heat is exiting the system. So that's where we see our enthalpy change is a negative. We're giving it away. So we've got high energy reactants, low energy products. So to get from reactants to products, we have to get rid of some of the energy or give it to somebody else. So that's the negative enthalpy. For entropy, entropy is the measure of how dispersed energy is, or how spread out, or how messy that energy is in a system. And so in this case, we want energy to be spread out. We want it to be dispersed. Okay. So think about your room. So you've got your bedroom or your dorm room, whatever it is. You move into that dorm room and a month goes by. Does your room spontaneously get cleaner, or does it spontaneously get messier? Yeah, it gets messier, right? So all of that stuff that you packed into your room or into your dorm spontaneously comes out and is spread out all over the room. Well, entropy is very much the same way. Energy is very much the same way. So when things get messier, we see that entropy is a positive value. It's a positive change. Entropy is when things get messier. Messy is good. When things get cleaner, we see that entropy is negative. So nobody likes to clean. So cleaning is a negative thing. So when energy gets organized or energy gets forced into its place, that is a negative entropy change. When it spreads out or becomes messy, that's a positive entropy change. So messy is good. So we have the second law of thermodynamics here. Second law of thermodynamics tells us that the total entropy of the universe is always increasing. So in other words, the universe is always getting messier, right? So if the entropy is increasing, we're going from here to messy. So the total entropy of the universe is always getting messier, is increasing. Now, the universe is a big place, right? So the universe is something that's really hard to wrap our heads around. So what we're going to do is we're going to study entropy as it has to do with a chemical system. So often we do a lot of our experiments in a beaker. So we're going to talk about entropy within the realm of a beaker, within the realm of a chemical reaction. Okay. So the entropy of the universe is going to be the system plus the surroundings. So the universe is a big place. It's going to be the system. So us as chemists, our system would be what's happening in the beaker. What are we interested in? And the surroundings would be everything else. So the room around us, the table underneath the beaker, anything that's touching that beaker would be the surroundings. So we know that the universe, our system, and everything else, we know that that's always a positive value, okay? So if system plus surroundings is greater than 0, it's a positive number, then the process is spontaneous. If the number is a negative number, so system plus surroundings ends up being a negative number, then the process is non-spontaneous. Okay. Like I said, we don't typically study the universe in chemistry. We leave that for the physicists. In chemistry, we're really going to be focusing on just the system piece here. So changes in chemical entropy. So chemical entropy, so the change in entropy, and I could put Rxn down here for the reaction. So change in anything is always final minus initial. So entropy again is independent of path. We're not going to look at how it gets from point A to point B. We're just going to simply look at the 2 points. We're going to look at the final, so after the reaction has taken place, the reactants. We're going to look at the products. We're going to look at the initial, before the reaction takes place, the reactants. And we're going to look at the difference in those two scenarios. Okay. So some things that will change, will increase the entropy. So remember, increase the entropy means it's getting messier. So what are some situations where from reactants to products we get messier or we disperse energy more? So reactions whose products are in a more random state. So going from an ordered solid then to a liquid, that would cause the entropy to be positive. So think about a solid is in a fixed location. Liquids are free to move relative to one another, so slip and slide past one another. So where there is more opportunity for things to get messy, they will in fact get messy. So going from an ordered solid to a little bit more free liquid, that would cause an increase in entropy. And then going from a liquid to a gas would offer us more opportunity for things to get messy. So remember, liquids are very, very close together, still some pretty strong intermolecular forces. We move to a gas, those particles spread out dramatically. Intermolecular forces goes down dramatically. So going from a relatively ordered liquid to a completely dispersed gas would also cause an increase in entropy. More opportunity for messiness, it's going to get messier. Another example would be reactions that have a larger number of molecules in the product, okay? So let me grab my stylus here. All right, so an example of a reaction would be something like this. So if we've got 3 molecules of ammonia, and that breaks down into nitrogen and 3 molecules of hydrogen. So what we're looking at here is just simply the number of particles, the number of compounds. So in this first reactant side, we would have 3 of these NH3 molecules. Okay, so we have 3 of these molecules present. When we go to the product side, we have 4 molecules present. So we've got N2, and then we've got 3 molecules of H2. So here we've got a total of 4 molecules. So reactions that have a larger number of product molecules than reactant molecules. So more things means more opportunity for mess. So when there is an opportunity for things to get messier, they will in fact get messier. So having a greater number of particles on the product side is going to cause an increase in the entropy. Okay. So thinking about the state, solid, liquid to gas, thinking about the number of particles, 2 versus 4, or 3 versus 4. And increase in temperature. So an increase in temperature will also cause entropy to increase as well. 2 different ways to think about this. So if particles are moving faster, the faster a particle moves, the more randomly it will move. And so more random, faster, more opportunity for messiness, and it will become messier. So that's one way to think about it. The other way to think about it is typically when we see an increase in temperature, we're likely going to see a change to the state as well, so solid, liquid, gas. So 2 different ways to think about that. But increase in temperature also means an increase in entropy. And then lastly, solids dissociating into ions. So this one's very much related to the second one. So for example, if I put NaCl solid into a beaker of water, it's going to break apart into sodium ions and chlorine ions. So again, we've got 1 solid molecule to start with, and we've got 2 molecules on the other side. So we start with 1, we end with 2. That's an opportunity for messiness. So that certainly is going to cause the entropy to increase as well. So just some things to think about, some examples, concrete examples to think about when we think about changes in entropy. Okay. So let's dive into this idea of solids, liquids, and gases just a little bit more before I wrap up this section. So when there is a state change, what chemists talk about is that there are more places to put energy. So if there's more places for that energy to go, for it to disperse into, that's going to increase the entropy. That's going to increase the messiness. So what does it mean to have more places to put energy, more opportunities for messiness? Well, if we look at solid water, so ice here, in a solid block of water or in an ice cube, those water molecules are in a fixed position. So the only place that they can go, the only energy that they can exert is just a vibration in place. So they can vibrate back and forth in place, but they can't move anywhere else. If we think about those same water molecules in the gas state, those water molecules can vibrate, they can oscillate, they can rotate, they can transition from one facing one direction to facing another direction. So there's all different kinds of ways that they can exude their energy, or they can move around or wiggle around. So when we go from a solid to a liquid to a gas, there's more opportunities for those particles to wiggle around, more opportunity for energy to be exerted, and therefore it's going to get messier. Entropy is going to go up. So let's think about the following example. So I'm going to give you a few seconds to think about it, and then I'll dive in and talk about it. So is entropy, so we're just looking at S, delta S, is entropy increasing or decreasing? So here we're looking at water to water, or H2O to H2O, that's how I should say it. The big take home here is gas to liquid. So going from a gas to a liquid, those molecules are becoming more ordered. We're cleaning them up, right? We're organizing those particles. So in this case, entropy would be decreasing or going down. Cleaning is bad, so entropy would be a negative number or decrease. What about this one? All right, so the first thing we need to know is what is sublime. So it's when a solid carbon dioxide goes to a gas. So again, we're asking about a state change here. So solid to a gas, is that going to increase entropy or decrease entropy? Yes, it is going to increase entropy. So solid, very organized, gas, very dispersed. So those particles are going to spread out to become messier, and the entropy is going to increase. What about this last one? All right, so here, if we look at the states, so state is gas, gas, gas. So we are not changing state, so we can't think about that. What we're going to have to look at here is the number of particles. So on the reactant side, I start with 2 particles. On the product side, I have 3 particles. So in this case, entropy would be increasing because I go from 2 particles to 3 particles. So more opportunity for messiness. The messier it's going to get. All right, so last thing I want to talk about before I wrap up this section, is the third law of thermodynamics. So we had the first law of thermodynamics, energy is neither created nor destroyed. Second law, entropy of the universe is always increasing. We're always getting messier. And the third law of thermodynamics is that for a perfect crystalline structure, so a perfect molecule at absolute zero, so when Kelvin equals zero, the entropy of that particle would be zero as well. So all particles are in exact positions, all positions are occupied, and nobody is moving. This is a hypothetical place. We haven't gotten to 0 Kelvin. We've gotten really, really, really close, but we haven't actually stopped the movement of particles. So we hypothetically have not reached 0 Kelvin, and we also have not reached entropy equals 0. But if we could reach 0 Kelvin and we had a perfect particle, entropy would be 0. Okay. We live in reality. So in reality, we were either going to have an imperfect crystal. So that's one thing that can change. Or we will not be at 0 Kelvin because we haven't reached that yet. Okay. So why is this important? Well, it gives us a baseline. Anything above this is going to be becoming more entropic, or the entropy is increasing. Anything below this, entropy is decreasing, it's becoming messier. So this hypothetical place gives us a baseline, gives us kind of a starting point to jump off of. Okay. What we're going to do with this starting point, this jumping off point, is we're then going to talk about standards. So if we know our baseline, then we can start to develop standards and rely on tables of information to calculate entropy rather than always having to experimentally determine it. So that's the end of this video, just an introduction to entropy. I hope you guys found this helpful.